is Caleb Flanagan, and I am the group leader for Group 1, and today I'm going to show you all the Flanagan experiment. So the objective of this experiment is to determine the latent heat of vaporization using the Flanagan equation, and we also want to observe how the changes in the saturation pressure and temperature will affect the latent heat of vaporization. So a little background and theory on the equation is it is an example of how the change in property that cannot be measured directly can be determined from the measured pressure and temperature. And so out of the manual, the equation for the Flanagan equation is dP sat over dt equals SFG over VFG, which is also equal to HFG over T VFG, where P sat is the saturation pressure, T is the saturation temperature, HFG is the latent heat of vaporization, and VFG is the specific volume. And then also SFG is the entropy. For an ideal gas, the equation is as follows: dP sat over dt equals SFG over VFG, which also equals HFG times P sat over T squared R, where R is the ideal gas constant. Oh no. Another thing popped up. So the apparatus and equipment, so over here we have the diagram, and so they're all labeled and stuff, but so number one is the beaker, and it's sitting on the hot plate, and when you turn it on, it starts bubbling the water. And number three is the thermocouple that is going to read the temperature and send it to the computer. 4 and 5 are the transducer and the pressure gauge. The transducer will read the pressure and send it to the computer again. Then you have your air bleed valve and your vacuum control valve. The air bleed valve obviously lets you control the airflow, and the vacuum and the pump help you create your vacuum, and then you just have your water reservoir and then the computer system. So the setup and preparation of the experiment. So first you're going to connect the thermocouple and the pressure transducer to the data system and open up the PDAC. And then you're going to make sure all of your equipment is connected correctly and reading the right measurement. And then you just wait for your instructor to start the real experiment. So once it gives you the okay, you're going to place the beaker filled with 2 inches of water on the hot plate and place your thermocouple in the water. And then you're going to close your vacuum valve, open the air bleed valve, turn on the pump, and then open the control valve back. And then you're going to close the air bleed valve and make sure that the pressure in the beaker drops. When the pressure in the beaker is very slow, you're going to actually close the vacuum control valve again and then turn off the centrifugal pump. And then the next thing you want to do is turn the vacuum pump back on and bring the blast to the lowest vacuum possible, and then leaving the vacuum control valve open. Then you're going to want to plug your hot plate in and turn it to the highest setting so it starts boiling. And then once the water starts to boil, you're going to begin logging your data. And then once it's boiling steadily for a little while, probably like 20 seconds or so, you're going to slowly close off the lines to the vacuum that causes the pressure to rise. And then you want to open the air bleed valve back again, and then you can stop taking your data when the water reaches that rolling boil. And then you want to turn your hot plate off, don't touch it, make sure the beaker's cooled off, and you're going to start disconnecting all the power and cleaning up your work area. So one of the requirements I had to do was create this saturation vapor plot, the saturation pressure versus saturation temperature. It was taken out of the thermodynamic textbook. I think it was table A4 and A5, and I just had to create it in Excel. And as you can see, as the saturation temperature is rising, so does the saturation pressure. The temperature is in Celsius and the pressure is in kPa. Some calculation requirements. So I used the equation from earlier and I rearranged it to find the latent heat of vaporization. And then you use some values in the table to solve that equation. I did it for 3 different pressures and 3 different temperatures. And you can see that my calculated enthalpy is slightly higher than the tabulated enthalpy for all 3 cases. It's not much, between 20 and 30 kilojoules per kilogram height. left off that unit on accident, but yeah, so. So some lab safety you need to consider is slip hazard in case somebody spills the water, drops a beaker, breaks the glass on the ground. Just don't slip and fall. There's some burn hazards from touching the hot plate or touching the hot beaker while the water's boiling, so just don't burn yourself. And the last slide is my references. So I used the lab manual given in Moodle, and then I used the thermodynamics textbook, and I used table A4 and A5 for the saturated water temperature and pressure, which I used to create the plot. And yeah, I use that for the equations. And that's it.